Our speaker today is Apoorva Khare. He has been awarded the Shanti Swarup Bhatnagar Prize, which is India's highest science award. Recently, he received the Ganit Ratna Award for 2024-25, another well-known award. He is a fellow of the Indian, he's a fellow of the Indian Academy of Sciences, and he has been listed as one of 75 scientists aged under 50 who are shaping today's India. We are honored to have him come and give a talk at the Graduate Center today, and he works in many areas of mathematics, and today he'll be speaking on the history of majorization inequalities. Apoorva, the floor is yours. Thank you.
Thank you, Sandra, for thoroughly embarrassing me. I have no idea this wasn't enough. So yeah, it's always a pleasure to be back at CUNY and of course in Manhattan. It's a wonderful place to walk around, as I was just doing. So yeah, so today's talk is about majorization, and if you take away anything from the talk, let that be the stuff in the first 5 slides or so. You should go away knowing what majorization is, like absolutely knowing it. So, and because a month ago I discovered, or maybe less, that majorization is really prevalent in economics. And I didn't know that. So I want to tell you about majorization, starting with economics and then going on to the maths part.
Okay. I hate to interrupt you. I
Yes,
did press record, right? The audience
Yes.
yes. Okay, thanks.
Let's see.
Gave us a message.
Okay, yeah, it's recording. Yeah.
Yes, pause or stop
Okay,
recording. So
great.
we are in record mode, and let's see if the clicker works. Should I do full screen or no? This is good enough for recording. So yeah, so majorization. So first of all, majorization is some kind of partial order about real numbers, but really it's comparing tuples of real numbers. So 3 tuples and 3 tuples, or 4 tuples and 4 tuples. Okay, so yeah. So for one number, we say that A majorizes B if A is equal to. So that's hardly anything interesting. For 2 numbers, it is that the biggest of A's, so basically arrange them, sort them, and the biggest value is bigger than the biggest. The sum of the top 2 is bigger than the sum of the top 2 with all the partial sums. Right? And the total amount is the same. So that's the same thing that will happen in general. For general, then you first sort them down and then say that every partial sum from the top is bigger than the same amount of partial sum from the top. And equality for K equal to M. And if this equality part is removed, then we say that A weakly majorizes B, and you denote it with the W. So in some sense now, so first of all, right, so if I add 5 to, if I have these things, right, I add 5, A1 plus 5, A2 plus 5, B1 plus 5, B2 plus 5, then clearly this inequality stays the same, because I just added 5 everywhere. And this inequality stays the same, because I added 10 everywhere. This equality. So adding or subtracting the same real number from every coordinate in both sides doesn't change majorization. So I might as well assume that all the numbers are positive or non-negative. So all of the AIs and all of the BIs are non-negative. And now if you think about it, you have sort of a total amount of the total content is the same. Right? So that's like saying I have some sort of finite amount of money, economics, right? And then on both sides. And somehow I'm comparing 2 different distributions of that money or of wealth, right? So that's where there's actually a picture. I will show you a picture, but that's where we are going. And it's easier to show you with partitions, like Young diagrams, than to tell you with words. So I'll show you that. So first of all, now, where did the word majorization occur first? So it occurred in this famous book of Hardy, Littlewood, and Polya called Inequalities. And the word majorize occurs there first, of course, with an S, not a Z, because it was England. And so this is the following the equivalent. A majorizes B if and only if B belongs to this convex hull. Right? Can I use this thing?
Yes.
Okay, so I will tell you, I'll just write down a very simple thing. So B belongs to the convex hull of these guys. So what is this? So B equals summation, let's say lambda, so let's call it C sigma times sigma of A. Right? That's what we are saying. Sigma is in Sn. That is the same as B is majorized by A. Right, but now sigma of A is the same as just the permutation matrix sigma, P sigma, right? So C sigma times P sigma. So here, of course, all the C sigmas are bigger equal 0 and summation C sigma as well. Right, so complex combination. But that's the same as this thing. And now, of course, because every multiplication is associative, I can take this first. This matrix, this is a matrix, n cross n, applied to this. So does anyone know what all the convex combinations of permutation matrices are also called? This is a famous result of Birkhoff and von Neumann. It's called after them, and these are precisely the doubly stochastic matrices. The matrices is all row sums 1 and all column sums 1. So B less than A is the same as B is a doubly stochastic matrix times A. Right? So you can think of this in terms of pictures or in terms of linear algebra, and it's the same thing. Okay. And if and only if, to connect it to the weak majorization part, A weakly majorizes B, and negative A weakly majorizes negative. And sort of this is one way is clear, because if A weakly majorizes B, then all the partial sums in decreasing order are bigger, and the total content is bigger than the total content. On the other hand, the total content of minus A is bigger than the total content of minus B, so the total contents are equal. That's the majorization. So one way is just easy, right? Okay, now, and this is the picture. So this is the picture side of this. So if you have, say, y1, y2, y1 is the bigger of the two coordinates, y2 is the smaller. So, and then I apply all the possible permutations on two letters. So that will be y2, y1. And the set of all vectors majorized by this or by this is precisely the complex sum inside the bottom. And the same thing in 3 dimensions, so y1, y2, y3, you take the S3 orbit, take the convex hull. These are all the x's that are majorized by y. So that's the picture. And so if you have done some Lie theory, then this is, of course, the while group in type A. So you can ask what happens when you work with other while groups and do this. Somehow nobody had asked this before 4 years ago. But then Colin McSwiggan and Jonathan Novak introduced this idea and studied W majorization, where you replace the symmetric group by other while groups. And they studied majorization, W majorization in symmetric spaces of non-compact type and stuff. So it's a very nice paper in INRN. You can look at it. Okay, so this is the old stuff. So Hardy de Polya. So this is the book. And since that book, at some point, Ingram Olkin and with Marshall and Arnold wrote this massive 800-page tome on majorization and so many different applications. So to matrix theory, to spectral theory with eigenvalues, to of course, to inequalities of real tuples, to functions acting that way, Schur convex functions, and so on. This is an amazing treasure. Both of these books are treasures. The idea of this book was to collect all known inequalities until that time. They really amazing books. Okay, feel free to ask questions, obviously. So where does it occur in nature for us? So if you think about two n tuples of real numbers where the total sums are the same and they are not necessarily ordered, then certainly one setting is where you have eigenvalues and diagonals of a symmetric matrix or complex permission matrix. Eigenvalues are all real by the spectral theorem and so on, and they add up to the same thing. And then, for example, let's look at this eigen. So this is a rank 1 matrix, determinant is 0, so one eigenvalue is 0. And what is the other? The trace is 2, so the other eigenvalue is 2. So you have 2, 0 and 1, 1. So this majorizes, I'll write that. 2, 0. So you have an example of majorization, so maybe the simplest one. Right? Okay. And so now you can, of course, ask if the same thing is true in general, or at least can one characterize. Given two real tuples, eigenvalues, and diagonal entries, does there exist a Hermitian matrix so these have to be the diagonals, whose eigenvalues are those? And the answer turns out to be if and only if the eigenvalues majorize the diagonals. And this is a famous theorem by Schur and Horn. So when Schur was using majorization, he wasn't using the partial sum bigger than partial sum. Schur was using this, the Birkhoff von Neumann. There is a doubly stochastic matrix, so that lambda times the doubly stochastic is equal to D. So that was the way he operated. And Hardy, Littlewood, and Polya, they were the ones who proved that definition is the same as the partial sum definition. Okay? And this thing actually has a lot of stronger analogs or versions in geometry. Some of them are here, I guess. Or maybe these are strong versions. I don't know. Yeah, so anyway, so certainly majorization occurs sort of very fundamentally inside matrix theory. And I will say no more about this, but I'm trying to complete a paper where we actually make use of this fact and apply it to symmetric functions. So, but we will get to that in a few months. Okay, and now for the economics part. So, well, I will not show you the picture because that's too tempting to look at. But think of, so basically, as I said, we are comparing two different distributions of resources, of wealth, or whatever. So there are n people, each of them, I can raise the level so all the numbers, coordinates are non-negative. There are n people, each of them has some amount of money, let's say. Okay? And I'm trying to compare the inequalities. I'm trying to compare the distributions using majorization. So suppose everybody had the same amount of money. Okay? And then you'd say, okay, I have this population of one country, everyone has the same amount of money. If I plot the cumulative population, so cumulative to the lowest half, how much of the total money do they have? And the answer is half, because everyone has the same amount of money. The lowest third, or the bottom third, if you will, sort them, list them in any order. The bottom third has 1/3 the money. The bottom half has 1/2 the money. The full has the full. So if you plot the cumulative population versus the cumulative money, wealth, you get exactly the y equals x line in a utopian setting. Of course, as we all know, the reality is far, far different. And so you have inequality. So the bottom half has very little money and the top few people have lots of money. And that's how it is. This is the United States 10 years ago. And and it's curious, but this part says that 11% here is negative money because they owe things. So this curve actually goes below the x-axis here and then catches up all the way. So from 0, 0 to 1, 1, you can normalize so the total money is 1. Do that. But it starts going negative, and so this is really wealth inequality, right? And so there was an economist, Max Otto Lorenz, in 1905, even before Hardy Littlewood, Polya, or Schur, and so on. He had the idea to plot make this cumulative versus cumulative plot, and so the Lorenz curve is named after him. This is from Wikipedia, and now that's so like there's a correlation coefficient for a distribution or for two distributions. There is something called the Gini index of a distribution. It summarizes something like this. So, yeah. So majorization is really used to compare, or you can use it to compare income inequality across populations. Right? So I have two different populations. Let's normalize the total money to one. I say one of them is more unequal than the other, or one of them majorizes the other. So majorization is inequality. If, whatever, that definition. And so, so in particular, if you're stealing from the rich or taking from the rich and giving to the poor, then you're actually doing anti-majorization, and that was being done in the 1300s by Robin Hood. So as I said, so 6 marks. So if you can stop here and take this message back with you, then I will think my talk has gone by. Now for the actual math part, but yes, this is more interesting. I'm just fascinated by the fact that I didn't know that, there's so much of economics. This paper of Lorenz is cited so often. The idea of Lorenz dominance is basically majorization, and so on and so forth. Okay, so now let me show you the same thing in pictures that we all sort of know. So partition of an integer is a weakly decreasing tuple of non-negative numbers, integers which add up to d. So you can think of this as just a picture, or you can think of this as three people. One has $5, one has $3, one has $1. Okay? That's the way you arrange them in decreasing order of wealth. So let script PD denote the partitions. Then because they're already arranged in decreasing order, this is a majorization is a partial order. And I gave you three definitions. One was a doubly stochastic one, or the convex hull. One was with tuples, and one was with weak majorization, plus and minus. Here's a fourth equivalent characterization. Lambda majorizes mu, so two partitions. And remember, the total content is the same. So the total number of cells is the same. So they both have to have the same number of cells. Lambda majorizes mu if and only if mu is obtained for lambda by a sequence of downward slidings. Meaning what? Meaning somebody who is richer gives $1 to someone who is poorer, but without, or a bunch of such operations, but without sort of changing the order of richness. So 531 can become 441 because that's fine. 441 can become 432 because again, They still stay in decreasing order of wealth. But now look at this. If the richest guy now wants to give $1 here, he cannot do that because that's changing the order of inequality. But what they can do is they can push it 2 cells down. They can give it to the next richest guy. And 333 is certainly. And then you can check. So 5 bigger than 4, 5 plus 3, the partial sum bigger than 4 plus 4, bigger equals, and total content is the same. Similarly, 4 bigger than 4, 4 plus 4 bigger than 4 plus 3, so on. So this is majorization, and it is a characterization. So it's the same thing as majoring. And now if you think about it, 3 people having 5, 3, and 1 is somehow in unequal wealth. And you cannot, if you just want to stick to 3 columns, 3 rows, then you cannot go better than this. No more wealth giving across 3 people. So this is somehow the most equitable wealth distribution. It is also somehow the uniquely lowest element in the majorization order for 3 rows. But of course, then one person can give money to a 4th person. So right now you can think of this as 3 people having $3 each and a 4th guy having nothing. And now you can give $1 to the 4th guy and keep going. So if you think of keeping going, what is the last partition you would get? All the way at the bottom here. Since there are students. So you just get it. You just get one full column. If there are 9 people and everyone has $1. Or there are 900 people, the top 9 have $1 and no one else has any money. But that is still the most equitable if you think in dollars and not cents, right? And similarly, if you can go back and go reverse the process and start giving money here, the most unequal population, the distribution is where one person has all the money and no one else has anything. So let me write that down. So we will call that as lambda max and lambda min. And lambda min. This is people use this multiplicative notation for partitions. And everything in PD sits between lambda max and lambda min. Okay, so now that
kind of a dumb question, but if you made it like rather than decreasing, increasing, then the most equal thing would be the best rather than the worst. Is there
It's just a matter of reversing the.
Is there any historical reason why they chose this one? Is this like I don't want to make it so the most equal ones?
Hardly readable in Polia, yes.
It chose that arbitrarily. There's no.
I think because they introduced the term and the definition. So yeah, that's true. Okay, I think the purpose of this talk is to explain why this really is not less equal. So that's the goal of this talk. Yes, that's the right thing to say. And the goal of this talk goes back to Newton. Well, no, so Newton did what you were suggesting and he was wrong. Is the goal of this talk. So let's get there. Yeah. So how does majorization connect to symmetric functions? Right. So to the functions, these are polynomials which are symmetric in the arguments. So Newton's inequalities is a famous example. So let P be negative real rooted, which means if I take the negatives of the roots and call them plus x1, this is P minus x1, P minus x2, dot, dot, dot. Then first of all, I can expand these and the coefficients now are precisely the elementary symmetric polynomials. Fine. In the negative root, so if the roots are negative, then minus xi are positive. So all these ci's are positive. Great. So these are Newton's inequalities. He proved more than 300 years back that Ci satisfy this inequality. And this is called a sequence C1, C2, Cn or C0, C1, C2, Cn is called strongly log concave if this holds for every I between 1 and n minus. If you remove the denominators, then this is called just usual log concavity or log concave sequence. The point is the strongly log concave implies log concave. So this is stronger. That's why strongly. How does one prove it? So this is very nice. So Newton, of course, had invented calculus along with Leibniz. So you have a calculus proof of Newton's inequalities. Very simple proof. So the degree of this polynomial is n. I'm going to differentiate this polynomial n minus 2 times in 2 stages. Okay? And remember, all the roots of the polynomial are negative. So now if I differentiate the polynomial, then you get a lower degree polynomial. And by Rolle's theorem, I guess, so again, all the roots are negative still. And you can keep going. So by Rolle's theorem, if you differentiate this polynomial, then I minus 1 times, then that's still real rooted, and all the roots are still negative. And now what I do is I flip the order. I reverse the coefficients. So I don't know what you call it, inverting, reversing something, the polynomial. So the inversion is basically the degree of this guy is n minus this. So take the polynomial 1 over t and now the coefficients are reversed. This polynomial is also negatively rooted because you're never dividing by 0. It's negative. So reciprocals are negative. And now I again differentiate this guy n minus I minus 1 times. So now I've differentiated a total of how many times? It's n minus 2. Right? I've differentiated this original n degree polynomial n minus 2 times because here the degree did not change from q. And I normalize by dividing by some coefficient because I'm differentiating so many times. So this is now what degree polynomial? It's a quadratic and it's real root. Now let's literally write down what this quadratic is. An explicit calculation tells you this is the quadratic polynomial and it's real rooted. So b squared 2 over this guy or this thing must be bigger than 4 times a times c. So b squared bigger than 4ac, the 4 cancels and you get Newton's inequalities. That's it. So of course, I don't think this was Newton's proof, but it's very cute that it can be done in like 3 lines, 4 lines.
Quick question.
Yes.
So the negative real root implies strong concavity.
Yes, strong
You
local.
need the negative. Like, what if it's just real rooted? Then it doesn't.
The problem is here, right? When you take the derivative, something can become 0. One of the roots can become 0. Then you cannot do this. And then you have to be more careful, I guess. Right? There might be a version of this with all real roots, but this is the version people sort of care about. But yeah. So now, but let me reformulate this. So in terms of symmetric polynomials, so remember that the CIs were the elementary symmetrics for the negatives of the roots. How many monomials are there? Well, EIs are excluding stuff, right? So that means if you have n things and you take 2 at a time, you literally have n choose 2. So in general, you have n choose I. x1, x2 plus x1, x3. You never repeat a degree. So n choose 2. Similarly, n choose I. So Newton's inequalities are really saying that these are about the normalized elementary polynomials because I'm dividing Ci by the n choose I. How do you get n choose I from this polynomial? If you set them all xi's to be 1, then there are n choose I many terms and each of them is a monomial in ones. So of course it's just 1. So if you add them up, you get n choose I. So literally if you divide this guy by n choose I, meaning ei of x by ei at 1, then you get Newton's inequalities. They just say that the normalized monomials squared beats this normalized times. And now I'm going to claim that this is actually a majorization. Where is the majorization? Right? So let's look at the simplest case. So E1 square is bigger than E2 times E0. So I'll write that down. And I'll write it down slightly differently. Let me write down E1 bigger than E2 is 0. And you can ask, where is the majorization? And the answer is yes, right here. So the subscripts are the 1 and the 1, the subscript of 2 and the 0, and it is going, it's going in the reverse order. This guy is here, this guy is here. So this was what you were asking. So this is the way it should go, maybe. The equal population beats the unequal one. But so now let me tell you why that's not the right thing. So, but first of all, you can, so this was just for partitions with 2 parts, 1, 1 and 2, 0, or I and I plus 1, I minus 1. So this partition majorizes that one, but the inequality goes the other way. So Newton's inequality said this beats this, but the inequality goes the other way. More generally, I can ask the same question for a bigger partition. Why 1, 1? Why not 7, 5, 1, 1? And then that's 12, 14. 14 and 7, 5, 1. So that's E14 normalized, read E7 times E5 times E1 times E1. Or more generally, if you define any E lambda according to this partition, so E of the first column, number of cells in the first row times E number of cells in the second row and so on. Indeed, this is true. Newton's inequalities are true in general. It took 300 years after Newton for somebody to do it. But so Cuttler, Greene, and Skandera, in this wonderful paper, showed that if you have any 2 partitions with the same number of cells, then E lambda less equals E mu, meaning that they are defined this way for all x positive. So you can just take strictly positive if you want the negative real rooted polynomial, but because these are polynomials, so by continuity, you can extend. Either way, if and only if lambda majorizes mu. And so as I said earlier, we will see later that we want this to be a bigger equals, not a less equals. We will fix it. So this is Newton's inequalities taken to the sort of one logical extreme, one logical end, is instead of looking at just partitions with two parts, you can look at the general partitions, and then like one of them can have two parts, one of them can have three parts. That's also fine. They don't need to have the same number of parts either. But as long as lambda majorizes mu, we have this reverse inequality.
So earlier in your talk, you mentioned other Weil groups.
Yes.
You have an analog of this outside.
This particular one, I don't know. The analogs would really be of Schur polynomials because they somehow come from representation theory.
Yeah,
You can do something in Weil groups, in other types. For this particular one, I don't actually know. I would have to see the paper to see.
Okay.
But I'm suspecting a bunch of things are not done in other D types. Okay, so I will stick to type A though, but look at other symmetric functions now. So Cuttler, Greene, and Skandera, in addition to proving various results in their paper, they also did a historical survey of who all have worked on majorization inequalities, and so with Newton, Maclaurin, Schhlomilch, Muirhead. So as Hardy, Litchfield, and Polya note, this is the first time an explicit majorization inequality involving partitions was stated and proved. Newton didn't state it that way, and even if he had, it was only for two-part partitions. But Muirhead did it in full generality, so Hardy, Litchfield, Polya say that that's maybe the first actual majorization inequality in the literature. Schur in the 1920s, so there's this 1923 paper, as I said, where he used the doubly stochastic matrices. I don't know how much, maybe he did something, but yeah. Okay, and so on and so on. There's, as I said, there's of course other Lie types. But let's look at two more from the above list, starting with, as I said, Muirhead's inequality. So you can talk of, so we have the elementary symmetric polynomials, where you take if you have 5 variables, you take any 3 at a time, multiply and add all these up. But you can do other things. So for example, if I have any number of variables, and then let's say I take 3, 1, I look at x1 cube, x2 to the 1, and then the other variables don't occur. But I need to symmetrize this, so I just look at I naught equals j, xi cube, xj. So that's a monomial symmetric function. Even if I had 3, 1, 1, I would take xi cube, xj, xk, and j not equals k. So then you can still, and then symmetrize it. Again, in the spirit of Cuttler, Greene, Skandera, or Isaac Newton, let's look at the normalized monomials. And now we can ask the same kind of question. So remember I said there was this lambda max and lambda min, the most unequal wealth distribution, and the utopian one. Certainly this guy beats this guy. So is it true that the monomial function for this normalized beats or is beaten by, either way, this guy for every possible input x1, x2, xn possible? And so what is the monomial function for this? It is x1 power n symmetrized. So x1 power n plus x2 power n dot dot plus xn power n divided by n, divided by the value at 1, 1 plus 1 plus 1. So divided by n. This one is literally just x1 times x2 times xn divided by 1. And so of course we know which one beats which one. This is called the AMGM inequality. And this was known to Euclid. And in Maxwellian, Colin Maxwellian, who I mentioned, his latest paper with my co-author Siddhartha Sahi of Rutgers, they found out that this was apparently known even earlier. There is some shloka, some sutra in Sanskrit a few hundred years before me, not too much before, where they're talking about building temples, it's from in ancient India, building temples on rectangular basis. And then there is something here about among all rectangles with a given perimeter, which one has the biggest or smallest area? That's literally AMGM, square. Anyway, so the point is the AMGM, of course, is a special case of majorization inequalities, and this was generalized by Muirhead. This is the inequality that first occurs with general partitions, with actually general, not like Newton where there's 2, 0, 1, 1. Even if you think of it that way. Here, Muirhead states and proves it in full generality. This is the theorem. The normalized monomial for lambda partition with the same cells as mu beats the normalized monomial for mu at every x positive if and only if lambda bigger equals mu. And apparently I was at ICTP for a month this summer, and one of the people there was from Brazil. He's now a professor, but he was in the Math Olympiad camp in Brazil. And I don't remember my time in the Indian camp, but he remembers his time, and he said that he knew this inequality in the Math Olympiad camp in high school. It was called bunching, the technique of bunching. I don't know, but that's, the Muirhead is apparently well known, even to high school students sometimes. So this inequality is in the right degree. Inequality. This bigger and this bigger is this. Okay. And just to tell you that this is in the right way, let me prevail the proof by majority. So there are one in this, we are tied at 1 all. I will give you a second one in the favor of going this way. Inequality going this way. And this is using Schur. So Schur polynomials are sort of arguably the most important one of them all. Some are more equal than others. So the reason why is because they represent characters of irreducible representations of semi-simple of GLN or SLN plus 1, or polynomial representations of either GLN or of the unitary group U of n over couples. So to define them, let me just show you how. So suppose I start with the shape. So I start with the lambda being 2, 1, 0. So remember, elementary E210 will be E2 times E1 times E0. The monomial 210 would be xi square xj to the 1, xj to the 0, symmetrized. Schur 210 is different. It's defined in a completely different way. You take a shape with take a Young diagram or Ferrer's diagram with 2 cells, 1 cell, and 0 cells. 2, 1, 0. And if I have 3 letters to play with, then the Schur polynomial 210 in x1, x2, x3, 3 letters, I do the following. I fill these shapes up with 1s, 2s, and 3s. The rule being across any row, the entries weakly increase. They are non-decreasing. And across any column, they are strictly increasing. So if I have a 1 here, so I cannot have a 3 here. Because if I have a 3 here, what do I put here? But I can have a 1 or a 2 here. So if I have a 1 here, then this guy can be 1, 2, or 3 independently of this guy. And this guy has to be a 2 or a 3. The 3 choices here, 2 choices here, that's the first 6 of these diagrams. 1, 1, 2, 1, 1, 3, 1, 2, 2. So that's the first 6. Notice, by the way, that, right. And the other choice is that I have 2 here, because I cannot have 3. In that case, this has to be a 3. And this could be a 2 or a 3. So these are the only other 2. And so that gives me 8 different fillings. These are called semi-standard Young tableau. Sorry if I'm repeating, everyone knows here. And then what you do is for this, you write down, I have to get a polynomial. How do I get a polynomial? x1 square x2, x1 square x3, and so on and so forth. And notice that both of these guys give you x1, x2, x3. So polynomials can have coefficients bigger than 1. So you literally write this down, and you can write this, and you can check it's symmetric, or you can check it factorizes, and this is symmetric, either way. This is the Schur polynomial, a Schur polynomial, and in fact, this is actually the Weil character formula. It's the character of a finite dimensional representation of SL3. 3 stands for this 3. And which representation? It's called the adjoint representation. You can also write this down as a ratio of 2 denominators. That is really the Weil character formula, because it's alternating sum over the Weil group Sn in the numerator and the denominator. But you can, so this definition is due to Littlewood, the same Littlewood as in Hardy-Littlewood-Polya, and that definition for the ratio of determinants is due to Jacobi, and that Schur used it in his thesis, and so on and so on. And Weil also worked with. Okay, so here is one Schur polynomial. Here is another. It's the same 3 letters, x1, x2, x3, 1, 1, 1. Well, then there's only literally one thing you can do. This has to be a 1, this has to be a 2, and this has to be a 3. You cannot do anything else. So this is the Schur polynomial. Same question. Does the Newton, Muirhead, Cuttler, Greene, does that inequality hold for normalized Schur polynomial? So meaning I have to divide this guy by 2 times 2, 8 by 8, and I have to divide this guy by 1. Well, so you might as well divide this by 2, this by 2, and this by 2. Is the product of these guys by 2 bigger than this? The answer is yes, if the xi's are positive or non-negative, because this divided by 2, a and gn, is bigger than square root x1, x2, square root x2, x3, square root x1, x3. And you multiply the 3 square roots, you get exactly this. So just by normal a and gn, indeed this is true. So you can ask the same question. There's the same thing that I told you already once for elementary in the reverse order, and once for monomials in this order. Does it hold in this case? And if so, does it hold in the correct way? See, I told you, proof by majority. So, Cuttler, Greene, and Skandera in their paper, they proved half of this. If there should be the same number of cells in the two partitions, if S lambda beats S mu for all x in the orthogonal, then indeed lambda is bigger than lambda majorizes. And they conjectured, they did not know how to prove this, but they conjectured that the converse is true. And then Sra, who is at MIT and at Munich, I just met him last month, he proved the converse is true. So, and for that he used something called the Harishchandra-Einstein-Zuber integral from mathematical physics or from representation theory. But this is what he. Great. So this is the result. And so now finally let us collect all those inequalities in one go. So Muirhead's inequality stated that a normalized monomial beats a normalized monomial if and only if lambda majorizes mu. Okay. Cuttler, Greene, Skandera, and Sra, they proved this beats the normalized Schur beats the normalized Schur if lambda majorizes mu. Very parallel. Newton and Cuttler, Greene, Skandera proved this guy normalized elementary here if and only lambda is majorized by mu. That's the different one. So naturally, the obvious question, is there some unifying phenomenon that specializes to all of these guys, these cases, and fixes this discrepancy? Obviously, something like that would be very nice. The answer is yes, and that is the purpose of this talk. They are all special cases of something else that arises with mathematical physics, probability theory, or Jack polynomials. So I'll just tell you what they are roughly, but I don't know them very well myself. The real expert on Jack polynomials among us probably Siddhartha Sahi, as you will see from the. So now we come to some work that I have done with Siddhartha Sahi, and some work that Siddhartha Sahi has done with Colin McSwiggan. So ours is a preprint from fall last year, and theirs is a preprint from I think May of this year, so just 2 months ago. So this is now we are literally at cutting edge. So Jack polynomials, first of all, are a family of symmetric functions with two things. One is the partition, like Schur, S lambda or M lambda. And one is this parameter tau. So tau is a real parameter. Tau is actually allowed to be infinity as well, as you will see. I'll give you the Jack polynomial for two variables, and you will see that tau can be 0 and tau can be infinite. Okay? And they do specialize to the previous three families: Schur, monomial symmetric, and elementary symmetric. And then this is like an info sheet on Jack polynomials. They generalize Schur polynomials, they generalize zonal polynomials, and they show up in multivariate statistics and random matrix theory as well. Often people use alpha, which is 1 over tau, to parameterize them. I think Macdonald's book, which is sort of the Bible of Jack and Macdonald's polynomials, uses alpha. We use tau. Sahi told us to use tau. So that's it. And they can be defined recursively using, see Wikipedia. Right? They can also be defined somehow using Gram-Schmidt. That there is some orthogonality with respect to some inner product. You do Gram-Schmidt, and this is the basis of whatever, something, of some space. Okay. So when tau equals 1, this specializes to Schur. So Jack polynomials where tau equals 1 are Schur polynomials, because Schur polynomials can also be defined using Gram-Schmidt for the usual Hall product, for usual inner product, usual Hall product, with tau equals 1, and so this is a generalization of the inner product as well, etc., etc. Okay, so here is the formula for two variables. It's explicit. So what you do is the following. Tau is, so you write this, so this is called the Pochhammer symbol or the rising factorial. So if you put tau equals 1, what do you get? You get 1 times 2 times 3 times k. So this is actually k factorial. So so this is the Jack polynomial. Every factorial is compensated either above or below by the corresponding Pochhammer symbol with the same length. And so you see now, if I put tau equals infinity, so if you have a tau equals 0, what do I get? I get, there is a tau square up top, because each of these has a tau. So there's a tau square here, a tau here. I cancel the tau, I get one more factor of tau here than below. So if I put tau equals 0, then all the terms where, these guys occur are 0. Which terms don't vanish? Well, the point is tau choose 0, a tau of 1 terms. The 0 tau is 1. So the extremal terms have tau 0 or tau 0 here. So the extremal terms don't vanish. And in that case, you just get 1, 1, and 1. So whatever. So you get, in the extremal case, tau equal to 0, you get x, you get the external. That's literally the monomial function. X something, y something, xy flip the other. When tau equals 1, then as I said, all these parameters are just I factorial. And so what you get is this cancel, this cancel, this cancel. You literally get just the geometric sequence, finite geometric sequence. And you can check that this is the Schur polynomial. How do you check this is the Schur polynomial? Well, you have A and B, right? So you have B is smaller. Maybe I'll do this here. Let's just do a 5, 3. Right? So now if I have AB, then I have two variables. I have to fill up these three in this way. And now I'm left to fill up this guy. This could be either 1, 1 or 1, 2 or 2. So what do I get? I get x1, x2 cube and x1 squared plus x1, x2 plus x2 squared. That's the finite geometric sequence you see over there. That's the Schur polynomial. And you can imagine this happens in both generality for two variables. If tau goes to 0, as I said, then you have the external terms like this, and then there's this extra factor of tau when you cancel stuff out. So this all vanishes. And so therefore, this is just the, so when tau equals 0, nothing here remains. You just get the monomial symmetric functions. And if you see the title of the slide, I said yes. So Jack polynomials do specialize to Schur and monomial, and the inequalities for those go the correct way. And what do they do about the elementary symmetric ones that causes the inequality to flip? That is when you take tau going to the only natural thing you can think of, which is to infinity. And notice that because each of these guys is a monic polynomial in tau of degree k, so degree I plus degree this by degree this, you basically literally don't do anything, right? It's literally monic divided by monic, and you just care about the highest degree terms. So that's 1, the ratio is 1. So because of this ratio being 1, you literally get a minus b factorial, you get the binomial coefficient. And so you get this side, right? And now what is that? So that is literally E. So it's not we were hoping for like EA and EB because it's A and B, S of AB, monomial AB. EAB will be EA times EB. You don't get EA times EB. You get E2 to the something E1. Only E2s and E1s. Let's write that down. Let's draw that picture. So erase this in here. Right? So instead I'm getting something, so in here, so A is 5, B is 3. I'm getting E2 power 3 times E1 power whatever, E1 squared. So if you think of what just happened here, let me draw the diagram. There are 3 2s. And then there are 2 1s. So I started here and I ended up here. How did I end up here? So how do you connect the two pictures? That's also easy. So but what you end up with is literally the transpose of the other line. And this is the case in general. This is not just true for 2 variables, it's true for any number of variables and any number of any partitions. Right? And this, not only is this the reality, it also helps fix the discrepancy. Because lambda less than mu in the majorization order is the same as lambda transpose mu. So transposing reverses the majorization. And so now with that, we can write down the correct 3 inequalities in this way. M lambda bigger than mu if and only this, S lambda bigger than S mu in the same way, E lambda transpose bigger than E mu transpose if and only if the inequality gets reversed here, first of all, that is Newton reverses the inequality. But transposing also reverses the inequality, so further one more. And now you see the right hand sides are all the same. Lambda majorizes mu. The left hand sides are M lambda, S lambda, and E lambda transpose, but that is a good thing because these are all the specializations of Jack. So if you reformulate using the normalized Jack divided by the value of 1, then these guys are literally just, all of them are saying that for tau equals 0, this one, tau equals 1, and tau equals infinity, we have this inequality. P lambda normalized at that value of tau bigger than P mu, if and only lambda bigger than mu. So this part is, of course, again, this is the fact that Jack specializes to all these was well known. So none of this is new, but maybe making this connection or observing this all was probably not done before, and it leads to the natural conjecture. Is it true for every single value of tau? Why for only these three? What's so special about this? I could take tau equals 5, or tau equals 1/2, tau equals pi. Is it true for the tau equals pi Jack polynomial that this happens? Natural conjecture, and that's the, so now we come to our work, and what's the time? Okay, yeah. So let lambda and mu be any two partitions, same number of parts. The following are equivalent for any fixed tau. This is a conjecture. This is a conjecture. For any fixed tau, tau naught, we have this beats the the tau naught Jack polynomial normalized beats the tau naught Jack polynomial for mu normalized at every x, either all positive or all non-negative. If and only if lambda major equals mu. And then there is a third condition which is sort of weird. Okay? If you take an indeterminate, now think of tau as a variable. Remember I had these monic polynomials in tau above and below. So for an indeterminate tau, if you evaluate this thing at each x positive, then you get that the difference is a rational function. I will show you this in an example. But the point is this condition is extremely strong. Just think of it that way. This is a very, very strong condition. And so what happens is, suppose this is a rational function. Okay? If I now evaluate this at a tau naught, so I'm evaluating at both x and at tau naught. If I evaluate a tau naught and all these guys are positive coefficients, then I get a positive real number by a positive real number. So I just get that this is bigger equal this. Meaning this minus this is bigger equal 0. When I specialize not just to an x here, but also to the tau naught. So 3 implies 1 is clear. 1 implies 2 is sort of asymptotics. So 1 implies 2 is sort of some kind of asymptotics about growth condition. This is exactly the asymptotics that Cuttler, Greene, and Skandera had sort of used for Schur polynomials. But the claim is that the same asymptotic, Cuttler, Greene, Skandera's result for tau naught equals 1, holds for every fixed tau, the same asymptotics. And then like Cuttler, Greene, and Skandera, we can ask the conjecture that Sra solved, which is that 2 implies 1. At least 2 implies 1. That was what Sra. But we want to, of course, prove 2 implies 3, which is even stronger condition. So if you can prove 2 implies 3, then of course 2 implies 1. So, but what we could prove only was that if there are only 2 variables, then this is fine. Then we can prove 2 implies the strongest condition of all. We could not prove it beyond 2 variables. And it is still open even for 3 variables, even now. What is known is that 2 implies the weaker condition. 2 implies 1 is now proved for any number of variables. As I said, this paper of ours was 2025, late 2025. Very recently, in May, Siddhartha Sahi went to Taiwan and he was visiting Max Wigan, who is a faculty there now, and they proved 2 implies. So at least what Newton did, what Maclaurin, what Muirhead did, Cuttler, Greene, Skandera, Sra, all that stuff just cares about these 2 parts, not this algebraic, the coefficient-wise positivity of some polynomial. And that part is now fully resolved. But still, 2 implies 3, and we don't know this even for 3 variables. We do know this for 2 variables. And I'm hoping that it's true for 3. But maybe like the Jacobian conjecture, AI will come up with a counterexample for 3 variables. So even now, Jacobian is not known for 2, but it is known to be false for 3 variables and numbers. Right now, we know it's true for 2 variables. We don't know what happens for 3 variables and a
And is the rational function in and in mu 2 variables?
It has to, yeah, absolutely.
What does it look like?
So I will show you.
Okay.
So.
Nice.
So let's say lambda is those same 2, 0 and 1, 1. In that case, you can check that this is P lambda without the normalization at 1, without dividing by the sum of the coefficient. This is P mu. So if you subtract this guy, you get this. And now what we are saying is that if you evaluate at any xy non-negative, you get a positive coefficient rational function. That's all it's saying. Okay? So first of all, it's saying, so part 1, so this is part 3. For every xy bigger equals 0, this guy is a rational function with all coefficients non-negative. This is clear. But proof by observation. Right? Part 2 was just saying that lambda majorizes mu. And part 1, which is supposed to be weaker than part 3, says that if you evaluate tau, so you have this rational function where tau is a variable and these guys are fixed scalars. We have evaluated them. Now make the variable equal to something, equal to another scalar. If the scalar is 0, you get half. If the scalar is infinity, you get 1/4. And if the scalar is any real number, any positive real number, then you get some, not everything. It's a positive number. So what it says is that this positive number times this positive number is positive, non-negative. This says that this polynomial over this rational function times number has positive correlation. So this is clearly strong. Yeah. Of course, all the three things are true, when therefore any implications between them are true. But what happens in three variables? So clearly 3 is the strongest, it implies 1, and then you can check that somehow if you take the mapping products. Yeah. So our main result therefore says that 2 implies 3 for all lambda and mu. Siddhartha, Sahi and Maclaurin's main result says that 2 implies 1. But for, as I said, they do it for any number of variables, not just for 2 variables.
And if lambda and mu are more complicated, does the difference look the same with x minus y squared and some function of tau like that?
Nice question. I didn't work it out, but the explicit, I gave you the explicit form for lambda and mu, right? For this.
Yeah, yeah.
So you can in principle just put that into Wolfram Alpha or ChatGPT and ask him to give you the answer for simple values of lambda and mu and check if it, if x minus y whole square factorizes out. Right? Okay, so in the last part then, I'll just say something about weak majorizations. I won't get to Macdonald maybe, but because so now first of all, I should tell you that the conjecture for Macdonald polynomials, I'll just tell you in 30 seconds. They are generalizations of Jack polynomial. Jack polynomial is a one parameter tau. Macdonald has two parameters q comma t. They specialize to Jack, they specialize to Schur, they specialize to monomial, to many other things, right? And for Macdonald polynomials, again the same exact conjecture is true because you might as well ask if you know the conjecture for Jack. Why don't you upgrade it to conjecture for Macdonald? The same three conjectures and the same statements here are true. We could prove the same thing for Macdonald polynomials for two variables, the strongest version. And Siddhartha, Sahi and Max, we can prove the same thing for Macdonald polynomials. So even for Macdonald, which is a two-parameter generalization of Schur, and it is also a further generalization of Jack. It is the most general family people are usually studying these days in symmetric function theory. All of this slide is true. So that's all I will say about Macdonald. But now let me get to the last part, which is about weak majorization. So far we've seen Newton and from 1700s, Muirhead from 1900s, Cuttler, Greene, Skandera from 2000s, and Sra. And now several of these inequalities are unified into a majorization inequality, majorization for Jack polynomial. But there was this other weaker version where the total content need not be the same. So you can ask, is there a weak majorization along the lines of Newton or Muirhead or Sra and Cuttler, Greene, Skandera, the Schur? And somehow until 2021 there was nothing as far as we could see. And the earliest such inequality was from this paper that I wrote with Terita on, it was about matrix positivity and functions preserving it. But unexpectedly in that paper, Schur polynomials showed up among positive definite matrices. And when we did some determinant calculations, this is along the lines of Cauchy's determinant Cauchy's determinant identity or determinant formula. If you know of that. Anyway, so the point is, because that showed up, we started studying other related things in it. And one thing we proved was exactly the same thing like Cuttler, Greene, Skandera, and Sra. In their statement, if you remember, the normalized Schur is normalized Schur at x bigger equals 0, not bigger equals 1. So it's all the positive ortho. If and only if lambda majorizes me. But we are taking the sort of the log positive ortho. So the logs are positive. All the x's are bigger than 1. If you just take that much assumption, then you don't get the total content equals total content assumption conclusion. You just get everything else. And if you want to now say something about and x less equals 0, x between all the xi's in 0, 1 power n, that would give you that lambda is weakly majorized by mu, or minus lambda weakly majorizes minus mu. And together they would form lambda majorizes mu by the very first characterization I mentioned. So we say that here as well, but I won't get to that. The ingredients of the proof here are sort of this very, so I didn't realize the importance of this guy until the paper I'm writing right now, which in a few months will come out, or maybe next month. But this is, we find somehow in sort of mathematical physics kind of tradition, the first order approximation of the leading term of a Schur polynomial, of any Schur polynomial, and more generally of any generalized van der Waals determinant. Okay, so where the lambda, the powers need not be integers, they can be real numbers. There's an integral from mathematical physics and so on, Harishchandra and Zuber. And there is a Schur complexity result, basically by Schur in the 1920s. There was this paper that CGS also cited. So I will skip this part, but yeah, this is the part where I mentioned about this and this implies sort of weak majorization. This together implies majorization. But I will skip that because we are almost out of time. But you could ask therefore the same question. So I know that if I know that if S lambda beats S mu at 1, then lambda weakly majorizes. What about the other two families, right? Monomials and elementary symmetric for the transposed partition. Remember the transposed there? This was done, so before Chen and Sahi and I wrote a paper in 2025, they wrote the 2024 paper where they indeed proved reflectivities. E lambda transpose beats E mu transpose for all x bigger than 1, the same bigger than 1, log positive opposite. If and only lambda weakly majorizes. If and only if the monomial is the monomial. Again, normalized monomial, normalized elementary, normalized Schur. So indeed now, the moment you have all these guys and our result, the analogous conjecture is again natural. And the same, I will write down the same slide once again. The same three things happen, except that now the only thing you replace is x bigger than 1 instead of x bigger than 0, and you add the word weak. And it's the same results. This is the same conjecture, it's the same results. 3 implies 1 implies 2 always holds, and if there are 2 variables, then 2 implies 3. And once again, Siddhartha, Sahi and Maclaurin prove the same result for 2 implies 1. So again, 3, this algebraic kind of condition of non-negativity of coefficients remains open for 3 variables. I mean, 2 implies 3 remains open. And 2 implies 1 is true for any number of variables just 2 months ago. Yeah. So this is all sort of, but this is sort of bringing to a conclusion a very nice unification of inequalities that had been around from Newton in the 1700s, Muirhead in the 1900s, and then Sra and Cuttler, Greene, Skandera in the 2000s. And this is all true for any Jack parameter. As far as I know, we don't have this analog for Macdonald polynomials. This is just for Jack polynomials. Okay, and the last part, which I said I'm bringing this paper out hopefully next month or in a few months, hopefully next month. So I will end with something that is not yet even cutting it, it's getting there, but there's a third version of majorization. I mean, an alternate form. Majorization is about adding the partial sums. You could multiply the partial sums instead. That is to say, you take logs of the amounts and then you add up the logs. That's the log of the multiplication. So, and that is called log majorization, or if the total product is not equal to the total product, you call it weak log majorization. The equality of total products is the log majorization without the word weak. So these majorization or weak majorization results compare, what do they say? I say I fix 2 partitions, lambda and mu. I look at a normalized blah in lambda versus a normalized blah in mu. Evaluate at all possible vectors. I can do the dual. I can fix 2 actual arguments, A and B, with positive, let's say positive coordinates. And I can evaluate blah lambda at A versus blah lambda at B for all different lambda partitions. That's the dual picture. And now this is, so it's forthcoming work with my student Sujit Damase, who, And so he's actually very talented. He just got a Fulbright and he will be spending the next entire year at MIT working with Henry Cohn on sphere packages. He just got the visa appointment form today to wait. So he's busy doing that, but so he will be, he'll be here next year. So fix A and B, which are, let's say non-negative, or you could say positive if you want. The following are equivalent. There is a constant. So look, I'm not normalizing here. I'm not normalizing with a value at 1. So if you think of, you can take the denominator and push it on the other side, and this could be like, S lambda at 111 divided by, that would not make sense. Right? So there would be something to do. So there's some normalizing constant such that this happens. Instead, I could just take this to be 1 as well. I could just say, what about S lambda of B? Let's equal S lambda. That's also fine. But yeah, so it's if and only if A weak log majorizes B, which means that these partial products are bigger than the partial products. If and only if, why should you only go for Schur polynomials? You can take any Jack parameter, and there's a polynomial in that parameter. That's it. Sorry, there's lambda. This lambda is the whole point. There is no lambda. It's independent of lambda. Okay? So that for any partition, we have this. And okay, this is sort of, I mean, yeah, this is correct, but again, this is a typo. These should not be normalized because these weren't. And then this polynomial actually is 1. If I want equivalence, I need to take tau naught less than 1. So for tau naught less equals 1 and a non-normalized parameter, non-normalized Jax, this being 1 is it. Okay, so I think that's pretty much it. So I will just end with the references. This is Newton, Muirhead, Cuttler, Greene, Skandera. So there's a big time jump right first year and then, and the rest of them are all in the last decade or something. So with Sra, then this is the paper with tau. This is the W-majorization paper. The archive of Chen and Sahi, where they do the weak-majorization for monomial and transposed elementary. This is where we do the weak-majorization for Schur. And then this is where we make all the conjectures. And I did not have space to put Sahi and Maclaurin's preprint laws. There's a preprint from 2026 May. Okay, I guess that's it. Thank you.
Questions?
What were the ideas of the proofs?
Yeah, so one way is asymptotics and one way is the Harish-Chandra integral. So you have to prove something like the following. If lambda majorizes mu, then some S lambda is bigger than S mu. So, or if mu is majorized by lambda, then S mu is less than normalized. Such functions are called Schur convex functions. And this was the old result of, I think, Schur himself in 1923. There's a famous paper he wrote in 1923, in which he says that if a function is symmetric and it's convex, then it is Schur convex. Now, how do you prove that it's convex? If the function is continuous, which symmetric polynomials obviously are, then you need to prove enough to prove mid-convex. And so for the mid-convex, what Sra did was he said that the Schur polynomial with some van der Waals, with some constants multiplied above and below, equals an integral over the unitary group. Harish-Chandra integral. And if you write that it's e power trace of something, and so you're looking at e power trace of a plus b over 2 times something versus e power trace a and e power trace b. So yeah, so let me just write this down. So roughly speaking, the goal was to prove that e power integral e power trace of a plus b over 2 times some matrix x, which is Hermitian positive definite or something, with respect to some measure, the Haar measure on the group, yeah, is less equals e power trace of ax. Yeah, and the e power trace of b. Something like this. And basically, this is just AMGN. Yeah, there's a value of the function here, value of the function here. That's basically just the angle. So he reduced it to AMGN. That's how it works. The hard part.
And in other types, you would presumably just replace.
In other types, you have Aristotle. That's exactly what these guys were doing. Yeah. But so the point, yeah, for majorization, exactly. And then you can try to do it with so for the analog, what is the analog of Jack polynomials in other types? Those are called sort of hypergeometric functions or Heckman octogroup and other stuff like that, which I don't know so well, but Sahi, of course, the expert, an expert. So that's how he and Maxwell proved everything in general. But the problem with Jack polynomials is you don't have this kind of a unitary. So you have to do some other things to make it work, and for Macdonald as well. So there are some interpolation formulas of Kunkov or Shantz cubes. That was what Sahi and Maxwell, Sahi and Maxwell used to finish the proof from Jack and Macdonald.
The Macdonald case is still over some finitely group.
No. So that's what there's no such formulas for Jackie, let alone Macdonald. But there is some interpolation formulas, and yeah, those are explained in Sahi and Maxwell's preprint. For and so they wrote 2 preprints. One was just over type A, where they finished off all this conjecture that we have. 1 implies 2 implies 1, and other stuff. Then they wrote the paper in the spirit of this paper in all lead types. That was both papers are, I think, from this like now, last May, or maybe one in May and one in June. Very recent. Both are short. So it's very. So,
Any questions? Should we speak again?
that would probably
That's right.
stop recording.
Yes. Yeah.